Okay. So, as we see that last week we talked about the properties of discrete Fourier transform. So, we have said periodicity, all kinds of things we have discussed, and we have talked about the circular convolution, but all we have applied on a single dimensional signal. So, we said x of n. So, x of n is an one dimensional signal. If you see n is varies from 0 to n minus 1, let us say in x direction. This week, let us start with what will happen if my signal is two dimensional. So, what is there? Instead of x one dimension, I have a two dimension. So, what should be the Fourier transform or discrete Fourier transform of a two dimensional signal? That is called two dimensional discrete Fourier transform. This is very much important issue. So, as per the last week number, you can say 5 or week number 4, we talk about x of n, which is only one dimension, and we talk about DFT of an x of n, discrete Fourier transform of a x of n is x of k. So, if the signal is one dimension in time domain and frequency domain is also x of k, k is varying. So, in one dimension. So, I give an sequence, I get an sequence. Xn is also an sequence, capital Xk is also an sequence. So, that is called 1D, one dimensional discrete Fourier transform, 1DFT. So, what is one dimensional discrete Fourier transform? As you said that x of k is equal to n equal to 0 to n minus 1, x of n e to the power minus j 2 pi by n is the resolution in one dimension into nk. So, e to the power minus j 2 pi by n into nk is the Fourier basis function, which is called one dimensional basis function. So, that means how do we do that? We generate different frequency component and convolve with the original signal to find out whether the energy is there or not. That is my one dimensional discrete Fourier transform. Now, if I say my signal is changed from one dimension to two dimension. So, I have a signal with let us say x of n. So, x of n has a two dimension, not only n, I have an m and n. So, x of n is a series. Now, I have a matrix, m by n matrix. What is the example? Image. Two dimensional signal is an image. So, if I say an image, image is called spatial signal, because it is if the f is called signal. So, image is a function of x and y. X, it has an x axis, it has an y axis. Mainly it is started from here, image we always started from the top corner. This is called x axis, this is called y axis, and this is called x axis. Okay. So, that is why f and xy is called spatial signal. It has a space that is plane, x and y two dimension. What is the concept? You know that a discrete version of an image, discrete version of an image is nothing but a pixel. A image is represented by a pixel, and every pixel has a coordinate in spatial domain x and y. Let us say x axis I have discretized in, I have taken n number of sample, and in y axis I taken n number of sample. So, if I say a pixel is a signal, So a pixels are varies along the x and y dimension. I discretize x and y dimension. So if I take an image, let's say 30 by 40 pixel image. So x dimension I have a 30 pixel, y dimension I have a 40 pixel. So how do I represent the signal? Is it nothing but a 30 cross 40 matrix? So I can write down it is nothing but a x of m and n, where m varies from 0 to let's 30 minus 1, 29, and n varies from 0 to 39. So m varies from m, if this is m and this is capital N, this is capital M, m varies from 0 to m minus 1 and n varies from 0 to n minus 1. So I have a signal in spatial domain. People say, why should I be interested in image transformation in frequency domain of the image? Why do I do that? Many times in signal processing, it is required to represent the signal in frequency domain. So I have a signal in spatial domain, which is the original image. I can transfer to a frequency domain and do some operation and again take the inverse transform, again I back the spatial domain signal. So suppose I have an image, I want to remove the high frequency component of that image. So I think all of you have known that what is the concept of frequency in a spatial domain signal. Concept of frequency in one dimensional signal, you know how the signals are varying. So if the more frequency means more rate of oscillation. Similarly in spatial domain also more frequency. So if I take a only white, let's say I take an only white image, what is the frequency? It is nothing but a single frequency or DC value. Or I take a black image, whole image is black, same black color. So all pixel value is same value, 0, 0, 0, 0, 0, 0, 0. So it is nothing but there is no frequency. But once the value of the pixels are changing in x and y direction, then I can say an image has a frequency. So if the change is very high, then we call the high frequency image. So suppose I want to remove those high frequency. So I converted the image to a transfer domain using two-dimensional discrete Fourier transform, then do some operation on it and again inverse transform, I get back the spatial domain image. So how do I do the two-dimensional Fourier transform or discrete Fourier transform? So two-dimensional discrete Fourier transform, DFT is defined by this or this, both you can write. What is the difference in both the cases? The normalization is done in frequency domain. So when I convert it to the time domain, so this is inverse IDFT, the normalization is not there. Or I can say that I do not include the normalization in here, so I include the normalization here when we transport to the again spatial domain. Both I can use, doesn't matter. Or I can do the normalization like this way also, multiply by 1 by root over of mn and again time domain also multiply by 1 by root over mn. So it is nothing but a gain, DFT gain. Okay, forget about that. Then what is happening? So if I have a signal in, so I have a signal in, if I have a signal in x of n, if I take the n point DFT, so single dimensional signal, I get x of k, which is called 1D. Only one dimension signal is changing. Now I have a signal which is x of m and n, both the dimension exist. So if both the dimension exist means, let's consider, first consider it is a single dimension. Let's say x of m, m is 0 and n is varying. So what is an image? Image is a value on this axis and value on this axis. okay or not. So, this is a spatial image. So, I first take those samples. Let us say those are varying 0 to n minus 1 and do the DFT. So, let us say I have taken, so what should be my DFT? That I will get an x of k for every m, let us m equal to 0, I get x of L. So, this I transport to DFT, discrete Fourier transform, I get this x of L. Now, what is this signal? This signal is nothing but again a signal which this signal is frequency transform, but this direction it is not frequency transform. So, first row wise I do the frequency transform. So, I write down the m in here. For every m I get the x of ml. Then I do the m wise, for every L I do the frequency transform. So, I take again one dimensional DFT. For every m, then I get x of k and L. Since the spatial domain signal has a two direction, my frequency domain signal also has a two direction, k and L. It is also a matrix. So, if I say what should be the final representation? So, I know x of k and L should be, you do not have to remember it, it is nothing but a, so first I said the n varies from or m varies from 0 to m minus 1 and then n varies from 0 to n minus 1, x of m and n e to the power minus j 2 pi. So, the frequency resolution, if I say I take m and m cross n point DFT, that means x axis is the m, order is m and y axis order is n. So, this is my y axis and this is my x axis. So, x axis order is m, y axis order is n. So, x axis I have an value k. So, I can say m k divided by m plus y axis I have a value L, L into n divided by capital N. This is my basis function of 2D DFT. Is it clear? So, one dimensional is mk by m, two dimensional I have to again add another dimension. So, first column wise, then first row wise, then column wise, or first column wise, then row wise, whatever I can do. So, this is my two dimensional basis function. Now, this basis function has in two part, one is real part, and so you know that e to the power minus j theta is nothing but a cos theta minus j sin theta. So, this part is real part and this part is imaginary part. So, basis function has a two part, one is real part and another is the imaginary part. So, you calculate x of kl, if I plot only real part of x of kl and imaginary part of x of kl, or the real part of only the basis function, either this or let us only the basis function real part if I plot, it will be look like this. If I plot the imaginary part of the basis function, it will be look like this. Real part is also a 2D and imaginary part also a 2D. That is the Fourier basis. Okay. So, this is one dimensional basis and this is another dimensional basis. So, they will be just repeated. Okay. So, this is called two dimensional DFT. Let us do an example, then we go for that other part. So, let us say I have a signal x of m n, let us say I have an image whose pixel are let us say 4 by 4 matrix. So, let us say 1, 2, 3, 4, and this axis also 1, 2, 3, 4. So 1, 2, 3, 4. Let's say this axis, then 1, 2, 3, 4. Again, let's say 1, 2, 3, 4. Again, this also 1, 2, 3, 4. Again 1, 2, 3, 4. 1, 2, 3, 4. So this is a 4 by 4 image. Those are the value of the pixel. Value of the pixel. So 4 by 4 image, each pixel is represented by 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So this is nothing but a x of mn. So can you compute x of kl? So x of kl is equal to m equal to 0 to m minus 1 into n equal to 0 to n minus 1 x of mn multiply by e to the power j 2 pi into, told me, km divided by capital M plus kn divided by capital N. So what I said, value of m is equal to 4, value of n is equal to 4. So what is the value of e to the power minus j 2 pi? It is nothing but a k into m divided by 4 plus k into n divided by 4. I can say e to the power nothing but a minus j 2 pi by 4 into k into m plus k into L into n, sorry, this is L into n. Okay. So what is e to the power minus? So I can say e to the power minus j 2 pi by 4. It is nothing but a, so it is cos pi by 2 minus j sin pi by 2. So this is equal to 0, this is equal to minus j. I can say minus j to the power km plus ln. Now I can calculate x 0, 0, k equal to 0, L equal to 0. I put k equal to 0, L equal to 0, and the sum, this will be, this part will be 1, this is nothing but a x of 0, 0. So you can say that all the sample sum. So it is nothing but the all 1 plus 2 plus 3 plus 4 plus 1 plus 2 plus 3 plus 4 plus 1 plus 2 plus 3 plus 4. So all the pixel value will be sum. Then calculate x 0, 1, calculate x 0, 2, calculate x 0, 3. Once you done that, then calculate x 1, 1, then calculate x. So now this is x 0, 0, 0, 0, 1, 0, 2. Similarly, x 1, 0, 1, 1, 1, 2, 1, 3, x 2, 0, 2, 1, like that way. So all the pixels, so this is also an 4 by 4 matrix, this x is also an 4 by 4 matrix, not 4 by 4 matrix, it will be how much, what should be the length of this matrix? This direction it is n minus 1, this direction is also it is m minus 1. n minus 1 value and m minus 1 value. So you can calculate that. Let us say the properties. So whatever the properties exist in 1D DFT, that is whole for 2D DFT also. So in case of periodicity, so if m and n is the DFT of two different direction, x direction DFT is m length and y direction is n length. So now if I say the frequency domain also the period is m and n. So f of uv, or I can say f of kl, whatever. So, u is the one dimension, v is the one dimension, u plus m into v is equal to f of u into v plus n is equal to this one. Similarly, in time domain also same. Here time domain I have taken KL. If it is I have taken Mn, then the instead of K it will be M and N. Okay. So, you can prove it. This is the proof. So, periodicity is hold in 2D also. Similarly, all periodicity in, let us say, another interesting thing you can see, that periodicity in 1D, let us say Fk is equal to f of k is one dimensional signal, the signal in k. So, instead of k and f of u is the frequency domain signal. So, this is the DFT, one dimensional DFT of length, let us say m. Okay. Now, if I say f of k multiply by e to the power j 2 pi u0 k by m. So, it is nothing but a shifting in frequency domain. That we have already proved in 1D. So, now if the u0 is equal to m by 2, so if u0 is equal to m by 2, then e to the power j 2 pi m by 2 into k by m. So, so I can say it is nothing but e to the power j to the power j pi to the power k. So, what is e to the power j pi? Cos pi minus j sin pi. E to the power j pi k. So, it is cos pi minus j e to the power sin pi. What is the value of cos pi? Is minus 1. So, I can put minus 1 to the power k. So, I can say this is nothing but a minus 1 to the power k f k is equal to f of u minus m by 2. So, if this is my f m by 2, if this is f of m by 2 and this is f of m, now if I say, if I put this m by 2 is u0 at the center, f of 0, let us say f of 0 at the center if I put, then if you see both the sides negative or positive is nothing but a sign change, changing the sign of every other sample, put f0 at the center of the interval 0 to m. Okay. You know that it is foldable. So, after every m it can be fold together. So, now if I say the same concept, if I apply for 2D, so this is my f0. Okay. So, 4 inverted point period meet here. So, this is my m cross n value, this is my m cross n value and this is my DFT period. So, why it is coming? Think about, you know, if you have a baseband signal is like this is my FM baseband signal. So, when you make the DFT, you get this one. Okay or not? DFT is symmetry at n by 2 point. Now, if you see, I have a 2 dimension. So, I have a this portion and this portion for 1 dimension. So, if I apply for 2 dimension, so in one page it will be 4 part. 4 part. So, that is why if you see, there is a 4 part. That is the periodicity of the DFT. okay or not? M by 2 point symmetry. So, this is one positive, this is one part and this is one part and this is one part. So, what do you know? F of n minus k is equal to nothing but a f star k, that if you know, complex conjugate. What do you mean by complex conjugate? A plus jb is my number, the complex conjugate is a minus jb. So, I know that from the DFT symmetry property, if it is one dimensional, then I know symmetry at here. So, if it is 2 dimension, I get 4 coordinate, m by 2 4 value. So, calculate it for an image and see what you are getting and then try to explain it. Then periodicity and spatial domain, you can also prove it, and then this is the example. So, if I say f of uv is my frequency domain representation of the image. So, this is the image. So, f of uv has a 2 part, again I can say like the x of k has a 2 part, mod of xk and the angle. So, phase and magnitude. Here also f of uv has a 2 part, one is magnitude real square plus imaginary square and has a phase imaginary by real. So, if I compute DFT of an image, then if I plot only the magnitude part, I will get this kind of image. So, this is the f of 0, f of u equal to 0 and v equal to 0. This is the center. So, this side it is n, let us say m by 2, this side it is m by minus m by 2, let us say, and this side is n by 2 and this side is minus n by 2. So, it is 4 point symmetry and this center is f0, because if you plot magnitude plot of a signal, you got this kind of plot. This portion and this portion is same. Now, this portion is the center portion m by 2. So, I make this m by 2 is my 0 point. So, this side is only sign change, this side is only sign change. Similarly, if I plot the only phase part, then also again get I this kind of image. So, this is the phase part and this is the magnitude part. Okay. Now, if I go translation, so instead of let us say here k minus m or l minus n, so this is nothing but a f of k e to the power j this part. So, it is nothing but a, so I take a shift in the frequency domain u minus m v minus l. Okay. Now, instead of k, let us k equal to r cos theta and l equal to r sin theta. So, instead of spatial shift, if I say the translatory shift, rotation shift I make. So, this is spatial, rotation shift. So, if it is rotation shift, then you can see the in the image in the translate domain, it is in frequency domain, it is also rotated by theta. So, that is called translation and rotation. So, if I shift, time shift, this is translation and I can rotate it also. So, if it is shift is theta, because it is in spatial domain. So, there is a rotation also possible. So, I can rotate or I can translate, both is possible. Okay. So, this is called 2-dimensional discrete Fourier transform. 2-dimensional discrete Fourier transform, I applied concept of single dimension into 2 dimension m and l. Okay. So, if this is my forward transform, this is my inverse transform. If this is my forward transform, this is my inverse transform. Okay? Thank you.